Since the early 1600s, telescopes have been the toolbox staple of the stargazer, used to pick out craters on the moon, the shapes of distant galaxies, and spy on the neighbours foolish enough to leave their curtains open. But if you've ever wondered what kind of sorcery could conjure a perfectly crisp image inside a tiny tube when all your eyes can make out is a wibbly smudge, then this is the video for you. To understand how telescopes work, we first need to understand why there's a limit to what we can see with the naked eye. When something is further away, it appears smaller thanks to perspective. And it also gets darker, eventually getting to the point where there's just not enough light bouncing off that object and reaching our eyes. So, better long-distance viewing relies on two things: gathering as much light as possible and increasing the apparent size of the distant object. One way of doing that is using lenses, curved pieces of glass that refract light, that bend it as it passes from air into denser glass. The first telescope was constructed around 1608 by a Dutch spectacle maker called Hans Lippershey. It consisted of two lenses aligned with each other, capable of magnifying objects up to 3 times. Light travelling from a distant object comes at us in parallel rays. When these rays enter the objective lens, that's the one facing the object, they refract. And because that objective lens has a bulging shape, it's convex, those light rays are bent towards each other. Inside the tube, these light rays converge until they meet at a focal point before then diverging out again. The thing is, with those light rays crossing over each other, the image is now upside down. Not to worry though, because when you're looking at space, there's not really an up or down, so it doesn't particularly matter. Now, the eyepiece lens, which I think you'll agree is a rather apt name for the lens closest to the eye, takes the now diverging light rays and straightens them out again, creating a virtual image on your retina. As this virtual image is closer to your eye than the real object, it has the effect of magnifying the image, tricking the eye into thinking the object is closer than it really is. The amount of light a telescope can gather depends on the size of the objective lens, and there are obvious practical limitations on how big you can make a giant lump of glass. The largest permanent refracting telescope was installed at the Yerkes Observatory in Wisconsin in 1897, and it has an objective lens over 1 metre in diameter. It weighs in at around 26 tonnes, but unfortunately it's one of those cases where bigger isn't necessarily better. Refractor lenses suffer from the problem of lost light. Some light that should pass through the lens actually bounces off it, just like when you see your reflection in a window. Not ideal when you're trying to pick out dim, distant stars. So the bigger you take the telescope and the lens, the more light escapes. The solution to this problem was the invention of the reflector telescope. Instead of bending the light with huge glass lens like a refractor telescope does, a reflector telescope uses vast curved mirrors. Different technique, but pretty much the same principle. Rather than a convex lens, which the refractor telescope uses, use a concave mirror to receive the light, whatever it's being pointed at. The bowl shape of this mirror reflects the parallel light rays at an angle, so they all converge at the focal point before then diverging back out again. Most reflector telescopes then have a secondary mirror to deflect the image sideways so you don't have to put your face in front of the mirror, which of course would get in the way of the actual object. Finally, an eyepiece lens magnifies the image just as with the refractor telescope. Using a mirror like this gets around the problem of unwanted light reflections, because all the light should be reflected. However, just as with refractors, to get a lot of light, you need a really big mirror. The good news though is that it's much easier to make a massive mirror than it is to make a massive lens. Mirrors simply have to be silvered reflective surfaces, and they don't even have to be a continuous smooth curve. The largest reflector telescope currently in operation is the Gran Telescopio Canarias in Las Palmas, which has a mirror that's made of 36 hexagonal segments. It's a whopping 10.4 meters in diameter. That's not the end of the story for reflector telescopes though. So successful are these giant mirrors that at least 3 more are currently under construction. Among them is the imaginatively named 30-metre telescope, and there are no prizes for guessing how big that one will be, and the superbly named European Extremely Large Telescope. I guess the 39.3-metre telescope didn't really have the same ring to it. Anyway, regardless of how big the mirror or lens on a telescope is, any scope on the ground will suffer the effects of atmospheric distortion, which can make any image of the stars look all wibbly-wobbly. Oh, that's not the scientific term. That's just a Greg term. It is atmospheric distortion that makes stars appear to twinkle when you look at them with your naked eye. And to avoid it, most research telescopes are popped on the top of mountains where the air is thinner and there's a lot less light pollution. There's one surefire way of avoiding atmospheric distortion, and that's to remove the atmosphere altogether by launching a telescope up into the vacuum of space. Now, hang on a minute, the almost vacuum of space. Light from other stars, or the light that gets reflected off planets, can travel undisturbed to the telescope. The Hubble Space Telescope, that was launched in 1990, is the most famous of these. It's a reflector telescope, and it's produced some of the most memorable images of distant galaxies and nebulas. And get this, outside of the haze of the atmosphere, it's able to pick out objects with an accuracy equivalent to seeing a firefly in Tokyo from New York City. Before I wrap this up though, I'm aware that I've only talked about optical telescopes, those that collect and magnify visible light, just like our eyes do. But there are a whole range of other ways to observe distant objects. For instance, there's the Spitzer Space Telescope. That's equipped with infrared cameras that monitor heat sources out in the depths of space. And the Kepler Telescope, that keeps a watchful eye on over 100,000 stars at once, using sensitive visible light photometers to try and detect the passage of planets. It's fair to say that the simple act of seeing far has come on leaps and bounds in the last 400 years. We've gone from a crude 3 times magnification to being able to see unbelievable distances in remarkable detail. Personally, I'm looking forward to the next 400 years of insightful telescope names. I'm rooting for the unthinkably vast telescope, or perhaps the fantastically accurate reflector telescope. You can work out the acronym for that one yourself.
The James Webb Space Telescope is revealing the universe like never before. Our planets, the furthest galaxies, and the strangest phenomena.
And what you can see is actually material falling into a black hole.
And that's only in the first few weeks. There's going to be a lot more discoveries to come.
The James Webb Space Telescope is a product of decades of hard work from scientists around the world.
I have been waiting my entire astronomy career for JWST. It is absolutely revolutionary compared to what was available.
It's very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy. And it just doesn't happen very often in the history of science, and that's really exciting and significant.
One of the things that makes James Webb so special is its gigantic mirror.
So that there are various things that make the primary mirror on James Webb special and incredible. I mean, the first is the sheer size of the mirror. It's the largest one ever launched.
The Webb mirror is around 6.5 meters in size. So if you can imagine that, that's bigger than most houses that you're walking by.
It's so large it wouldn't fit in the rocket, so they had to devise a way of folding it up so that it would fit inside the top of the rocket.
It's absolutely humongous. And that makes a really big difference in terms of the sensitivity of the telescope.
Well, it's thousands of times more sensitive than Hubble. It's a step forward of factors of 1,000 or more. Factors of several thousand, in fact. I'm correcting myself.
The bigger the mirror, the more light you collect. The bigger the collecting area, the more sensitive you are and the further you can see.
The other thing that makes it absolutely incredible is the precision with which it's been made. If the mirror was stretched to be the size of the United States and you were to measure the size of the biggest bumps and dips on the mirror, you're only looking at a bump or a dip of order 1 centimetre in size. It's absolutely incredible, and that's what generates the near-perfect images from the primary mirror.
But it's not just the mirror that makes the images from James Webb so incredible. It's also the type of light that it detects. The James Webb Space Telescope detects infrared light, which is a wavelength of light that we can't see, but the unique properties of infrared make it incredible for exploration.
So with the infrared light, you can see the atmospheres of exoplanets. There's molecules in star formation regions, things like caffeine and alcohol and water ice, the signatures of life around other planets.
So just a few things then. Infrared opens up the possibilities for astronomers like Olivia and allows them to capture images that would previously be impossible in the optical range. But even within the infrared spectrum, there are multiple different wavelengths. On board Webb, there are 3 instruments that observe near infrared. This is closer to the visible spectrum. But the instrument that's garnering the world's attention is the mid-infrared instrument on board JWST, known as MIRI.
MIRI is essential for JWST. Without it, you can't see the cooler phenomena in the universe. You can't peer back as into the earlier stages of star formation as you would like.
So MIRI is an incredibly significant and important instrument. The image contains far more detail than has ever been done before.
So when we look at it in a new wavelength of light, we find things that we hadn't expected to see, and that's a really important part of how you discover things about the universe.
MIRI allows us to see further along the infrared spectrum, and this in turn allows us to see through dust clouds and further back in time than ever before. That's because as galaxies move away from us, the colour they emit shifts further into the infrared, so the longer the wavelength we can observe, the further back in time we can see. But despite the capabilities of MIRI, it very nearly didn't make it on board James Webb.
So MIRI wasn't initially part of those plans because it seemed technically very complicated, and I think people were thinking about the science in a slightly different way. And so I started making the case that really we needed to add a mid-infrared facility to the telescope.
Gillian Wright is the European Principal Investigator for MIRI and the Director of the UK Astronomy Technology Centre, and was instrumental in pitching to get MIRI on board Webb.
When I found out it was confirmed that MIRI was going to be on board, I remember being very happy and also knowing that I was going to be very busy for a large number of years.
Gillian wasn't wrong. Construction of James Webb Space Telescope started in 2004, and 17 years of work later, on Christmas Day 2021, with MIRI securely on board, the telescope finally launched.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I've been looking forward for the Webb launch for many, many years. And as it got closer to Christmas Day, I was extremely nervous. I don't think my family enjoyed Christmas morning with me because I had on the TV the Webb launch playing, and I was quite nervous. I had my pillows ready in case I needed to hide.
Everything went perfectly. It was an incredible launch. It was a pleasure to watch.
So it was a very good Christmas present.
It was a lovely Christmas present, it really was.
Over the next few months, the James Webb Space Telescope travelled over 1.5 million kilometres away from Earth to its new home, gradually turning on the instruments along the way.
So then it was getting really exciting because we've been from Christmas Day all the way through until the late spring when MIRI finally gets turned on.
As the instruments are being turned on, it's both exciting and it's nerve-wracking because you know that there could be things wrong.
After decades of work, the James Webb Space Telescope was finally operational, and it wasn't long before the images started coming in.
I knew when Webb was going to take its first images, they were going to be spectacular. What had not prepared me was just how spectacular they were going to be.
The first images were just incredible, just so beautiful. It was amazing.
And then when the first images came back, I was just absolutely astounded at how good everything performed. And I've been smiling ever since. It's almost emotional.
The images are spectacular. And the only thing more spectacular than the images are the discoveries that lie within them.
So one of the things I think that's really exciting about the early images is the way they show how Mary really adds information.
I can see details in there that I knew existed, but I never thought I'd be able to see with a scientific instrument. Some of the first Webb images released were of the Southern Ring Nebula. This is a planetary nebula, which is a star at the very end of its life. In the mirror image, we see actually a second star. So we can see a red star and a white star. So these are actually a binary system, and that's the very first time we've seen this binary companion in the Southern Ring Nebula. This is an image of Stephan's quintet, 5 galaxies that are interacting with each other. And what you can see in this galaxy up here is actually material falling into a black hole in an active galactic nuclei. You can see the material in the galaxy is actually orbiting and falling into the galaxy itself. This is 13 times further than what we've been able to see before in the infrared.
I mean, JWST has already found the furthest galaxies we've ever seen, the highest redshift ones, the closest, and that's only in the first few weeks of operation, and that's really exciting, and I think it's an indication that there's going to be a lot more discoveries to come.
With Webb, we've designed it to answer many of the questions we already know about the universe. But as with all new telescopes, there's a realm of new discoveries.
The mysteries that will arise, I think they're really exciting.
New questions to answer.
The questions we don't know how to ask just now, and I think that's really exciting to see something that not only has nobody ever seen it before, but nobody expected to see it.
I feel very privileged to be part of this.
I'm proud to be part of JWST. It's been an amazing journey and a fantastic privilege, really, to be part of it.
I think it's just incredible. I helped make that instrument, and when I see these images, I'm just full of smiles.
The CAT-7 array of radio telescopes are listening for electrical signals that have travelled billions of light years and are infinitesimally weak.
And we need to be really far away from people and the things that they do, because anything modern really interferes with our observations. So people, the microwaves, their cell phones, their cars, all these things really drive us further and further away.
The data CAT-7 has already catalogued has increased our knowledge of the universe.
We've been imaging neutral hydrogen in our galaxy, we've been looking at transient events, we've looked at pulsars, but really we're limited by data. We need more data to do better science.
The signals Simon looks for are so small that despite a combined detecting area of over 1,000 square metres, these 7 telescopes capture just 2 megabits of data per second. And Simon's ambitions go far beyond that.
I think really understanding how galaxies came to be the way they are, the evolution of the universe, I think that's one of the most exciting things we can anticipate addressing. And it'll really answer the questions of how did the universe get to be as it is and where is it going? It's only achievable through big data. We really need to catalogue the entire universe. We have to figure out what it was like at every epoch. And that's the only way to really understand how it evolved and where it's going.
Life on the Karoo is about to change. These telescopes are set to be joined by more, thousands more. A new telescope array will fill the valley, covering a square kilometre, the biggest array in the world.
Over the next 10 to 15 years, this valley is going to fill up with telescopes. As far as the eye can see, you'll see telescopes, forming a vast array, bringing data siphoning back into the Karoo, where science is going to be done on an unprecedented scale.
Work has now begun on the array. The new telescopes will receive 30 terabytes of data per second. It will be the biggest data collector ever built.
We're moving into the regime of unprecedented amounts of information. we have to take a step back from the data and think, what are we trying to extract from the data? What is the information that's actually contained therein? And make sure that our tools and our techniques that we bring to bear look for the patterns in the data. And this really requires a new breed of astronomers to see how we're going to change from where we are now to this next big shift.
Simon Ratcliffe and his team have to develop a way to retain the important patterns in a huge flood of telescopic data. If they can do it, they will discover the greatest secrets of our universe.
Shep is an astronomer at the Haystack Observatory near Boston. But the 37-meter telescope here simply isn't big enough to photograph the black hole at the center of our galaxy. To do that, Shep needs a telescope with 100,000 times the resolution. And that requires a dish 4,500 kilometers across, roughly the size of the continental United States.
To observe the object that we're after, we have to create a telescope that can see finer details than any other telescope in the history of astronomy.
The reason you haven't heard about this massive telescope is because it only exists in Shep's computer. He hooked up radio telescopes from across the continent, effectively to produce one giant virtual dish.
The way a normal telescope works is it focuses all the light because of its particular shape into a single focal point. When you link telescopes around the world together, we don't have a lens. We have to do it in a supercomputer here in Massachusetts.
Shep's supercomputer, the correlator, pieces together the raw data from all his separate telescopes to build up a computer-generated dish the size of America.
The level of detail you can see with a single dish is limited by the size of that dish. But when you link telescopes around the world together, something magic happens. You create a virtual dish that's as big as the distance between those dishes. And that gives you a level of detail that's 1,000 times finer than you can get with a single dish.
Instead of creating pictures, each of Shep's telescopes produces reams upon reams of data.
And this is where we keep all of the data when it comes back from the telescopes. Each of these contains 8 very large hard disk drives. And when you have 2 modules together, that contains as much data as the US Library of Congress, which is the largest library in the world. And we have, on these shelves, about 64 such libraries. The amount of data is just staggering, really. We spend a lot of money in this project on disk drives.
There's so much data, processing just a few nights' observations takes months.
Hey, Mike, what's the latest from the correlator?
Actually, a lot of interesting things from last night. You've got a full hour of direct detections on the galactic center.
Oh, these are great.
Perfectly clear.
These are great. It looks like this is going to be a great data set.
That's right.
What about the other baselines?
Great.
Okay, that's excellent. That is just excellent.
Yeah. That's with zeros. That's with no corrections. So
that's beautiful. That is absolutely beautiful. There's going to be a lot of confidence we'll be able to do what we want to do.
Despite producing all this data, Shep doesn't yet have enough telescopes linked together to build up a full image.
Yeah, so this is a great data set. I'm very, very happy with this.
But this year, he might be able to detect our first glimpse of something that has until now eluded us: the shadow of the event horizon.
If someone were to say to me, well, that's impossible, you can't do it, I would say that's our job. Our job is to try to see things that can't be seen, to try to do things that are great challenges. The reason that we're interested in this is quite frankly because it's hard. And if you'd asked me 5 years ago if it was possible, I flatly would have said no.
As a space scientist, I've seen many mirrors coated in the past. But the people who've been given the daunting task of coating the James Webb mirrors are the technicians here at Quantum Coatings in New Jersey. And I'm about to find out how they do it. The mirrors have to be perfect. The tiniest speck of dust could be disastrous. So Quantum's lab is one of the cleanest rooms in the world. More spotless even than a hospital operating theatre. This hexagonal pane of glass is an exact template of the metal sheets that will make up the James Webb's mirror. They're made of beryllium, a very rare and extremely strong and lightweight metal.
That gun has dry ionized nitrogen gas. He's blowing the surface off. So this is our last chance to blow off any last remaining particles before it goes in the chamber.
The glass is then carefully placed in a large vacuum chamber. The mirror's in there now, everything's ready to go, and I got the pleasure of shutting the door. For 2 hours, all the air and any remnants of dust are extracted from the chamber, until finally the gold is added. Gold is used for the coating because it reflects infrared light so well, the part of the spectrum the James Webb cameras use for imaging. First, it's heated with a laser, vaporizing it.
How much gold are we talking?
The amount of gold that we evaporate is about 40 grams. The amount that gets onto the mirror is a quarter of that, just a few grams.
You must be talking about a fairly thin coating of gold.
To put it in perspective, one sheet of paper is about 1/1000th of an inch thick. We could fit 100 gold coatings into that piece of paper.
Into a single piece of paper?
That's right.
The result, one of the most perfect mirrors on Earth.
So here we are.
Wow. That is lovely. It's beautiful. It's just so smooth. I think I've never seen my reflection so clearly. I think the fantastic thing is the idea that this coating is going to be out in space and on sort of 18 mirrors like this is quite phenomenal.
It's quite a thought.
The 18 mirrors are hexagonal because they fit together more snugly than if curved. The hexagons also form a shape that is roughly circular, so focus the light evenly. These mirrors are typical of the James Webb. Every aspect of its engineering has been pushed to the limits of what's technologically possible.